Okay, so let me change this. Jess, I don't know how Mrs. Helene did things. I know in general, but for my class, I record all the lessons. So you'll see in Schoology within the Chapter 4 folder, there's a folder that says video lessons and slideshows. So if I use a slideshow, the slideshow will be in there later. If I record the lesson, I post the lesson later if you need to go back and look at it. The rest of you already know that, so here we go. Okay, so we want to talk about what's called the fundamental theorem of calculus. There's two parts to the fundamental theorem of calculus. I've taught them both ways, meaning I've taught the first part first and then the second part. However, what I've realized recently is that I think it makes more sense to teach the second part of the fundamental theorem of calculus first and then do the first part. The first part of the fundamental theorem of calculus is probably one of the more important concepts that we're going to deal with as far as integrals goes. Okay, and we'll get to that soon. Okay. So let's see, turn on my clicker. We're going to work a little bit with a definite integral, and we've talked about definite integrals already, but I know it was 2 weeks ago and it was a lot of work before then. But remember, we defined the definite integral as the area under the curve. And we talked about ways to approximate those areas by using rectangles, also known as Riemann sums. And then we talked about, well, how to find the exact area, but that only worked if we had a nice, pretty geometric shape. Okay, where the area under the curve is a rectangle or a trapezoid or a triangle, that kind of stuff. Today we're going to talk about how to find an exact area regardless of what shape the curve looks like. Excuse me. At one point in time, we're going to get to the mean value theorem, not today. I actually split this lesson into 2 days, so we'll get to the mean value theorem and some of these other things on Thursday. We'll talk about an average value. We'll talk about the second fundamental theorem of calculus, which is part 2. We're actually going to do those backwards. And then, as always, I would say, especially with the new year, try to be more positive. It's one of my personal goals, even though I started with a 20-minute rant. I apologize. Okay, so here we go. We've done this already, but we're going to talk about some little weird things that happen, and that is, we started with this concept that said if we take the derivative of an integral, we get back to the original function. And if we take the integral of a derivative, we get back to the original function. And you'll recall way back when we did that, one of them ends up with a plus c and one of them doesn't. Well, the difference here is you'll notice that I'm taking the antiderivative of a function f of t, and that variable is important. And when I take the derivative with respect to x from a to x, where a is any number and x is a function, the t's magically become x's. And so I'm going to ask you to just accept that for now. And then later on, you'll see why the x's or the t's become x's. But for now, we're just going to go with that. Okay? So the number at the bottom, the a, doesn't matter. It can be any number, positive, negative, 0. It's irrelevant. And the x is just plain old x. And again, when we take the derivative of the integral, we end up back where we started. So the t's become x's. Does that make sense? They're undoing each other with the new little subtlety that t's become x's. Okay. Now, what if it's not just x up on top? What if, for instance, I go from a to x squared? What if I go to a different function? Okay. This is the only thing that causes problems for people, and that is you have to remember that t's don't become x's in this case. T's become x squareds. Okay? So you'll notice that in this example, the square root of t squared plus 1 becomes the square root of x to the 4th plus 1. Because x squared squared is x to the 4th. And then there's this little bugger on the end, the 2x. That 2x is there because you have to chain on the derivative of this function up on top. And you always do that. If I go back to this example, okay, so x's, or t's become x's, and you chain on the derivative of x. What's a derivative of x? It hasn't been that long. What's a derivative of x?
1.
1, right. So there's a times 1 here. But again, we're not going to continue to write that times 1. That's ridiculous. But instead of breaking it into two instances where, oh, if it's only x or if it's some other function, you can just consider it doing it every time. Okay. T's become x squareds. You chain on the derivative of x squared. If I change this problem, same procedure. T's become whatever the thing is up on top. So I get x plus 2 quantity squared, square root of that, plus 1. And chain on, well, in this case, I just chain on a 1 again, because the derivative of x plus 2 is just 1. Okay? Makes sense. That's the second fundamental theorem of calculus. And normally, or traditionally, I should say, this would be taught second, but I find it more logical to teach the second part first and the first part second. Okay, now the next one's going to get a little weird. If you want to put your pencil down and just watch, that's okay. This isn't crucially important, but I do want to show you where the first fundamental theorem of calculus comes from instead of just making it magically appear. Okay, so I'm going to take you through. This is the proof of the first fundamental theorem of calculus, part 1. Okay, so we start with this concept, which is what we just did. If we take the derivative of an integral from a to x of f of t dt, we get f of x. Okay, so that we know that already. Then we take capital F and capital G. If you'll recall, and I'm sure you do, but we started talking about using capital letters to represent antiderivatives. So if I have a function lowercase f, its antiderivative is capital F. So we're going to say that f and g are both antiderivatives of the function f. The only difference is that they're separated by some constant. So it would be like, let's say our function was x squared. Then g of x would be 1/3 x cubed, where f of x would be 1/3 x cubed, whereas g of x would be 1/3 x cubed plus 7. So we're taking that same function, just sliding it up and down. Okay? So g of x is defined as the antiderivative of f of t. So the question would be, what is g of a? Based on step 3, what's the answer in step 4? See if you remember this from before break. No takers? It makes no sense to cross out an x with an x. I'm an idiot, sorry. What's the integral from a to a of that function f of t?
Is it 0? Because there's no area there?
Perfect. Okay. So going back to this would be equal to 0. Good. Okay, and that doesn't, you don't need to know the fundamental theorem of calculus to remember, like Prasad said, it's the area under the curve going from the same number is a rectangle with no width, so the area would be 0. Okay. Which means if I take this equation and I put a in there, I get g of a is 0, and then f of a plus c by plugging a into x. This is what we're going to use in a second. I needed to get that information. I needed to know what my integration constant was. Now, if I plug b in for it, I don't necessarily know what g of b is, except for the fact that if I come back to this guy again, g of b would be f of b plus c. And then doing a little bit of algebra here by substituting this into there, I get that. Which eventually gives us this. And this is the first fundamental theorem of calculus. This is what's going to allow us to find the area under any curve from an interval from a to b. What does it mean in English? It means take this function x, take the antiderivative of it, plug in b, plug in a, and subtract them. Okay, let me say that again. Take the antiderivative, plug in the top limit of integration, and subtract, plugging in the bottom limit of integration. Okay, so now we don't have to just rely on it being a nice geometric shape. We can do any function on any interval. Questions on this before I move on? Okay. Why isn't my clicker working? All right, we are currently experiencing technical difficulties. Please stand by. Get rid of this. Okay. So there it is, which we already knew. Okay. You have your lower limit of integration, you have your upper limit of integration. Remember that capital F is the antiderivative of lowercase f. So again, take the antiderivative, plug in b, plug in a, subtract the two, you're done. Okay. Quick. Yeah, go ahead.
So what, I'm confused what the integral like f of b and minus f of a, like what is that representing?
I'll show you when I do an example. It might make a little bit more sense. Okay, so hold your question, and then if my examples don't answer your question, we'll come back to you. Okay?
Okay.
So a quick review from when we started chapter 4. If we don't have limits of integration, we have an indefinite integral. So the indefinite integral, when you take an indefinite integral of a function, you get another function. Okay, what we commonly call the antiderivative. The antiderivative of x squared is 1/3 x cubed. When we put the limits of integration in, we get a definite integral, which means it's going to always be a numerical value. It's the area under the curve. So this is going to allow us to find the area under any curve from the points A to B. Okay. This is really big. This is comparable to being able to take the derivative of a simple function. So this is how we're finding the definite integral of functions without having to do any of the tricks like Riemann sums or any of that other stuff. Okay, so let's start with something simple. X cubed. You should be able to take an antiderivative of that. Allie, can you help me out there? What's the antiderivative of x cubed? It's been a while.
Oh, yeah, it has.
Putting you on the spot.
I remember you have to do something with like taking the opposite of the. So would it be like 1/3 x fourth or
Close.
second?
You have to raise the exponent first, then multiply by the reciprocal. So raise the exponent to 4, then multiply by the reciprocal.
X to the 4?
Right. Okay.
Okay, sorry.
That's okay. That's fine. I put you on the spot, like I said. Okay, notice the notation here. In this second statement, I have this bracket. What that bracket represents is I took the antiderivative, so this went away, but I haven't plugged in 3 and 0 yet. Okay? So the antiderivative, as Ali said, was x to the 4th, or 1/4 x to the 4th, or x to the 4th over 4. You plug in 3, there's my 3. You plug in 0, you simplify. 81/4. And that's the exact area under the curve. That's no longer an approximation. That's no longer based on a geometric shape. That is the exact area under that cubic function from 0 to 3. Okay, so think about that for those of you that are visual learners. We have this cubic, And we're going from 0 to 3. Now with the fundamental theorem of calculus, even though the top of that thing is a weird curvy looking thing, we can find the exact area under that curve. Whereas up until today, you would have had to approximate it using rectangles and a Riemann sum, or you would have had to hope that you could maybe get some type of geometry shape out of that, which we can't because there's no straight sides there. Okay, Marcus, does that answer your question?
Yeah, kind of. So like you do it so between 3 and 0. I still don't like completely understand like how that work ends up getting you the area under the curve, but
well, that's the basis of what an integral is. That's how we defined an integral.
okay.
Okay? All right, next example. Try this one on your own. Now, there's two things I'm looking for. One is seeing if you can still do an antiderivative because it's been a while. And the second one would be if you understand the fundamental theorem of calculus and are able to plug in numbers. Don't be bashful if you need to pick up that calculator to plug in chug. That might help for some of you that are struggling because it's been a while. When you have an answer or you think you have an answer, just give me a thumbs up so that I have an idea of 50% of the people think they have it, or 2 people think they have it, or everybody's good to go. You'll notice that when I rewrote the problem, I moved the 3 out in front because when we take the antiderivative with the constant, you could just move the constant out in front. So as I progress from here, I'm going to take my final answer and multiply it by 3 so I don't get that 3 wrapped up in any of the calculus. All right, Drew, let's pick on you. What's the antiderivative of x to the 1/2?
Is it 2x to the 3/2?
Close.
I'm not sure.
Now, you may have meant, did you already multiply it by the 3? Is that why you had 2?
Oh yeah.
Okay, my bad. So yeah, you are correct. Okay, so and that will make our lives a little bit easier now because again, I can pull that 2/3 out in front, and as Drew said, we'll just put the 2 out there and leave that alone. So then I just have to do this. And I'm going to write all the steps out, but as you get better and better at this, you'll be able to cut out some of the middleman here. So I'm going to take my final answer, multiply by 2. Don't forget about that 2. 4 to the 3/2 minus 1 to the 3/2. What's 4 to the 3/2? Is that the cubic root of 4 squared, or is it the square root of 4 cubed?
I think it's 8 because it's the square root of x cubed.
Okay, questions? Good. Yes, and as Max mentioned, this is the square root of 4 cubed. So you could either take 4 and cube it, 4 times 4 is 16 times 4 is 64, and then take the square root. However, I find it a lot easier to do the root first. So the square root of 4 is 2, 2 cubed is 8. Okay.
I'm sorry, isn't it, because I multiplied the 2 before and I got 15, but then I just realized you have to multiply it after you do the thing in the parentheses, sorry.
Yeah, yeah. Please excuse my dear Aunt Sally. Okay, good. Any other questions? Yeah.
I'm kind of confused. Like, I understand the process, but what happened with, like, the 3 and the 2/3? Like, I got 4.5 in front of my x to the 3/2. I don't know what I did.
6. Did you? Okay, so let's do some analysis here. Did you get this antiderivative?
No, that's what I'm confused about.
Okay, so we have to review the antiderivative process, right? So I'll give you the fancy schmancy calculus. The fancy schmancy calculus would be 1 over n plus 1 times x to the n plus 1. Okay, plus c. Oh, but wait, we don't have a plus c because we're doing definite integrals. Okay, but that's not the realistic way to do it. What we're doing again is take the exponent, raise it by 1, and then multiply it by the reciprocal of that number. Okay, so what Drew did is he took 1/2 and raised it by 1. 1/2 plus 1 is 3/2. That gives us this. And then multiply by the reciprocal of that number.
Oh, okay, thank you.
Got it? Okay. Any other questions? Life just wouldn't be the same if we did, there's all the work. Did I get 14? Yeah, good. Okay. Life wouldn't be the same if I didn't include some trigonometry for you. I'm sure you probably don't have them burned into your brain yet, but does anybody remember what the antiderivative of secant squared is? Anybody? Bueller?
Is it tangent?
It is. Okay. So the antiderivative of secant squared is tangent. We're evaluating from pi over 4 to 0. The tangent of pi over 4 is 1. The tangent of 0 is 0. And we get 1 as an answer. Now, the other thing to hype on is notice the notation. As soon as I take an antiderivative, the squiggly thing disappears. But I still have to indicate the fact that I haven't plugged in numbers yet. That's where the bracket comes from. And then again, the final answer. Let me reiterate, when you're taking an when you're taking a definite integral, you should always get a numerical answer. And what does that numerical answer represent? It represents the area under the curve. Okay. Last one. And this one I'm going to have to guide you through. I can't expect you to do this on your own. But there's a problem here. And the problem is that we've never learned, and we're never going to learn, how to find the antiderivative of an absolute value. Okay. So we have to approach it in a different manner. And remember, we talked about this a little bit, and that is, how does the absolute value affect a function? Now, this isn't just the absolute value of x. This is the absolute value of some other function. And I talked about, before break, I talked about where the absolute value of x graph comes from. Why does the absolute value of x look like a V? Well, remember, it is the graph of y equals x, where the negative part is flipped up on top. So the absolute value of any function takes the negative part and flips it up on top. So if we graph that puppy, we end up with something like this. It's that nice little parabola, x squared plus 2, or minus 2 minus 3, minus 2x minus 3, and then whatever was below the x-axis gets flipped up on top. And the problem is saying, okay, what's the area under the curve now from -2 up to 1, 2, 3, here? Okay, well, how do I do that? What I need to do is break it into two different problems. I'm going to start by finding the area of this region. And then I'm going to find the area of this region. And if I just gave you the antiderivative without the absolute value, this would be a negative area, because remember we said area below the curve, or sorry, area below the x-axis is negative. So if I just did it without the absolute value, I'd have to know, oh wait, I got to flip part of that over. And so I break it into two equations like this. This point I know is at -1, because you can solve that parabola to figure out where it hits the x-axis. And so this part of it is just a standard antiderivative. It's just the area under the curve from -2 to 1, and you can go and do the math for all that. That's not what I'm showing you here. It's not the mechanics of taking an antiderivative. I'm assuming that eventually you're going to get back to the 1/3 x cubed minus x squared minus 3x, and then plug all that in. And then notice what I did here is I just took the rest of that graph, but all of a sudden this changed. And how did that change? Well, I had to incorporate a minus sign somewhere along the way. Because again, originally that would be below the x-axis. I chose to incorporate it into the function. However, what I could have done is left this as x squared minus 2x minus 3 and just put a minus sign out in front. It's the same thing. Subtracting a negative area or taking the opposite of the function gets you the exact same results. It's just a matter of personal preference. Whichever one makes more sense to you and helps you understand the problem is what you're going to use. This one made more sense to me, so I went with that. Okay? So again, I don't care about the semantics of how to solve the problem. I just wanted to show you a weird situation that pops up when we have this absolute value thing. Because again, we're never going to learn how to take the traditional antiderivative of an absolute value. We're going to go about it with some sneaky ways. Okay, so now let's talk about some technology. Bust out your calculators. And depending on how new your calculator is, yours might look very different. So what I need you to do is hit Math 9 on your calculator. Okay, so Math 9 is FNint. For some of you, you're going to see this. It's going to say FNint. Others of you are going to get a picture I believe looks something like that, yes? Okay, so just so we're on the same page, does anybody have the FNint displayed on their calculator? Yes? Okay. Unfortunately, you have the older operating system. So let me deal with you guys first. If you have the FNint, you need to jot down and or memorize this notation. So after the FNint, you type in the actual function, whatever it is we're taking the antiderivative, and we'll do this as an example. Let's do x cubed dx from 0 to 10. Okay. So for those of you that have the FNint, you're going to type in x cubed, comma, x. It's always x, comma, 0, comma, 10. Lower limit of integration, comma, higher limit of integration, enter. Done. For the rest of you, I'm assuming that you're bright enough to figure out what you're supposed to do here. This is 0, this is 10, this is x cubed, and yes, you need to put an x in there. Why do you need to put an x in there? Because you have to tell the calculator which one is the variable. Okay, so Amanda, I saw you shake your head. Are you on the old FNint thing?
No, I'm on the new one.
You're on the, is anybody on the old one? Good. We're all new. Okay, so what's the answer?
So 1,500.
Can somebody confirm? Good. Okay. So this is an example of the technology usage. So back in the old days, before this little pandemic thing, as I mentioned before, the AP test had a calculator portion and a non-calculator portion. For our purposes, now we're assuming that it's all going to be calculator because they're not going to have a way to shut that down. So, for the most part, when we're learning this, I'm going to want you to actually do antiderivatives. But eventually, you're going to fn int everything. So for instance, if I come back to this problem, very first one we did, this guy, if you fn int that, okay, and I continue to use fn int even though that's not the notation, but that's what shows up. Math 9 is fn int. Typing that into your calculator quickly spits out 14. So there's going to be a desire to fn int every single definite integral that I give you from this point on. I would suggest that you resist that urge because you need to learn the mechanics just in case we get to something that is non-calculator based. If you rely on the technology too much and that technology gets taken away from you, you're screwed. Okay? So practice this by going through it the way I did it. You can always check your answers by fn inting. Or I might specifically say to you, fn int the crap out of this. And you're going to run into some problems that you, like for instance, this guy. Whoops. You can type that into your calculator as an fn int, and then you don't have to worry about how to take the antiderivative of an absolute value. By the way, absolute value, the easiest way I find to get the absolute value is to use the catalog down at the bottom, which is above the 0. So go second catalog, and ABS is the first thing on that catalog, instead of hunting around in all the menus for it. Okay? Questions on fn int? Good. Okay. And what they used to do when the test was split into two parts is they assumed that on the calculator portion of the exam, you never did a definite integral by hand. You fn inted everything. But that was having a non-calculator portion too. So we'll have to balance that between when to use it and when not to use it. But again, early on, especially on tonight and Thursday's homework where you're learning the whole process, I would suggest you do it by hand. But definitely check your answer with fn int. Okay, 2 more notes for you before we wrap this up. How are we doing for time? Okay, we're okay. We've talked already about how the definite integral is the area under the curve. Okay, so that was number 1. And you'll recall when we did derivatives, 3 things that the derivative represented. Now I'm going to introduce another concept of the antiderivative, or the integral. So we already know that the integral is the area under the curve. Number 1. However, number 2, I'm going to introduce it as an accumulator. Accumulator. Does anybody know what the word accumulate means?
Until I keep adding on.
Yeah, keep adding on to gather. Okay, so when we look at the accumulator here, if, for instance, I'm taking the antiderivative from 0 to 8 of this function f of x dx, what that means is I'm adding up area as I move from 0 to 8. So I start here at 0. And if I take the area under the curve from 0 to 0, we already talked about how you'd get 0. But as I start moving to the right, I'm adding up little slivers of area as I move further and further over. Okay? So in other words, when I get to this point, that area is a trapezoid. And then I add on a rectangle, and then I add on a triangle. But what happens here? Now all of a sudden, I start adding negative area, because remember, area under the curve is negative. Okay? So we could ask a question like, what's the max, or where is the max of that function? The function being the integral from 0 to 8 of f of x dx. And that's where the idea of an accumulator comes in. I start at 0 and I start adding positive numbers, so that area is getting bigger and bigger and bigger and bigger and bigger and bigger. Then all of a sudden I get to this point at 5. And I start to add negative area, so the total area is going to drop, which means, conceptually, that would be the max of that function. That's the easier of the two questions. The more difficult question is, well, where's the minimum? Well, then you have to start looking at the area under the curve versus the area above the curve. Is 0 the biggest, or 0 the smallest area, or is this area under the curve bigger than the area above the curve? Okay, and you do some geometry and figure that out. If the red area is bigger than the blue area, then 0 would be my minimum. If the blue area is bigger than the red area, then I went too far here. We're only going up to 8. Then 8 would be my minimum. But I think you can see by looking at the picture, the red area is bigger than the blue area. But it introduces a whole nother concept here of the integral being an accumulator of area as you move from left to right. Questions on that? Okay, last note, we do a little bit of physics. Displacement versus total distance. Before I give you this, let's review. Do you all understand the difference between displacement and total distance? Okay, so if you're walking back and forth, if you're doing a cha-cha, and you dance forward and you dance backwards, and you dance forward and you dance backwards, and then you end up where you started, my displacement is 0. I didn't go anywhere, even though I traveled a whole bunch. Or if you go around the block, your displacement is 0. Total distance is obviously the total distance that you traveled. So we've talked about the velocity function, and now we can incorporate integrals into that. If you want to calculate the displacement of a function, you can take the antiderivative of the velocity function. Now, why the antiderivative? Remember, we had the position function, we had the velocity function, and we had the acceleration function. If we go this way, we're taking derivatives. If we go this way, we're taking antiderivatives. So the antiderivative of the velocity is position. However, if you want to know the total distance, you got to slap an absolute value in there. Because we're counting both positive distance and negative distance as positive distance, so you add all that up. If you go around the block, and end up back at your house, your displacement is 0, but your total distance would be the mile that it takes you to go around the block. And we can easily calculate those using the calculus there. Okay? Make sense? Beautiful. We're done for today. So the beginning of the slideshow mentioned a couple other things, which is what we'll cover on Thursday. On Thursday, we're going to talk about something called the meltdown theorem. And we're going to talk about, which is also the mean value theorem for integrals. We're also going to talk about the average value of a function, which again makes no sense to you, but it'll be those last two components that we need for all this integral stuff. A lot of the homework for tonight is mechanical, learning how to take definite integrals. Okay, take the antiderivative, plug in b, plug in a, subtract. Okay, we good? Questions? Okay, everything else is the same. The calendar is still the calendar. We're still A day, so you get the problems from the calendar. The answer keys are in the folder. We're in a different Schoology course, but I think you should automatically be enrolled in it. I believe you guys are Spider-Man. I went Marvel this semester, so I believe is that right, Spider-Man? Okay. And we're good to go. Okay? Anything for me?
Yeah, I have a question.
Certainly.
I was just wondering if we could